Majority of what we're going to do today is not in the book. Little bits are, but the majority is not, and really shame on the book for not including this, because this is some of the coolest stuff in all of physics, I think. Right? So, let's just remind ourselves about light. How was it that we proved that light was a wave?
The double slit.
The double slit experiment, right? Okay, so now when we first talked about the double slit, we talked about these slits as if they were regular sized windows. Okay? So if you've got a regular sized window where the opening is like, a meter or so, and you're shining light through here, okay, what do you see on the wall on the other side there?
You're going to see like this.
Yeah, I mean, it looks like the light's just coming right straight through, and so you see a bright spot here, you see a bright spot there, which is not the diffraction pattern. And so what you might say, that proves that light is not a wave.
No,
what's the flaw in that?
Diffraction.
Yeah, the problem is that light has such a small wavelength, which much smaller than most people ever dreamed it could possibly be. So how does the relationship work? If lambda is much, much less than the opening, do you get a lot of diffraction or no noticeable diffraction?
No.
Okay, so you get no noticeable diffraction. Okay, so when scientists did this experiment with regular windows and they looked at it and they said, see, it's not a wave. Well, other people said, no, let's try it again with smaller openings. So then when we make these openings really small, like maybe a millimeter or so, then do we get this same pattern?
No.
No, what we get then is we get the diffraction pattern. Okay, so in those areas where you expected it would have been bright, it's actually dark up here and down here. And in the middle, where it should be shadowed by this central blockage, that's where you get the bright spot. And then you get another bright spot up here and down there, and then you get another bright spot up here and down there. And that is what we did that proved that light actually was a wave. Okay, so several years after doing this, some engineers got playing around, or actually some scientists got playing around with some toys that they had. I don't know whether it was because they were bored or because they had a reason to suspect that the universe behaved differently than they thought. Let me show you one of the experiments that they did here. And this is something that you guys should know really well. I want to build an electron gun. Okay, so a device that shoots electrons out. How would I do it? We talked about this, in TVs, in cathode ray TVs. How do we do it? Okay, so we're going to take a parallel plate capacitor. We're going to hook it up to a battery. And it doesn't have to be a super high voltage battery. I mean, we could use like a regular 9-volt battery, a little tiny 9-volt battery. In fact, let's do that. Let's say this is 9 volts. And so we're going to connect the plus side up to this plate, the minus side up to that plate, so we get a whole bunch of minuses here, a whole bunch of pluses here. We're going to take a wire and we're going to stick the wire in there, and we're going to run electricity through the wire with a different battery. Okay, so electricity is flowing through the wire, and if we heat that wire up, and if it has a nice little sharp bend in it, electrons are going to come off of the wire. And what's going to happen to that electron as it's floating in the space there?
Going to shoot towards the positive side.
Yes, it's going to be repelled by this side, attracted by this side. It's going to go shooting over here, and it's going to go thunk, which is not going to be a very useful gun. So how can we make this be a gun?
Change the path and then flip them back.
It's a change the voltage.
Okay, we could do that. Or how about let's just do something even simpler. Let's just, instead of having this be a solid plate, let's make this be like a wire mesh, like a window screen. So we can still charge it up with positive charges. Okay, so when these electrons come here, admittedly some of the electrons are going to hit the screen and go thunk, and that's the end of it. But some of the electrons are going to make it through the space in between them. They're going to come shooting out here, and voila, we have an electron gun. We can shoot electrons. Okay, so a bunch of scientists created this, and they got the crazy idea, let's shoot this at a diffraction grating. Let's do the double slit experiment. But instead of using light, we're going to use photons. Or, I'm sorry, try that again. Instead of using light, we're going to use electrons. Okay? All right, so if they take the same kind of diffraction grating that they use for optics, then what they found was that these things went straight through and they hit on the wall here, and someone went straight through here and hit on the wall here. So sure enough, we proved that electrons are little particles. Okay? But that was the same thing that we came up with over here when the window was really big.
Yeah.
Okay, so the scientist said, let's not jump to conclusions here. What if we use a really, really small diffraction grating, even smaller than the ones we're using for optics? What if we were to take a diffraction grating that's on the atomic scale? And what I mean by that is, let's call up Mr. Ramsey and let's ask him if we can borrow one of his crystals. He's got a great collection of crystals. What is the difference between a crystal and a rock? A crystal has a structure. I mean, maybe a better question is, what's the difference between graphite and diamond? You guys know that they're both diamond. Graphite and diamond they're both carbon. That's why my mouth isn't working right. They're both carbon. Okay? So graphite and diamond are both made of carbon, but they appear very different. They have great different properties. What is the difference?
Their structure.
Yeah. Okay, so diamond was formed under very, very high heat and very high pressures. And so when it formed, instead of having just molecules arranged at random any which way, like this is graphite, okay? With the diamond, the carbon molecules are in a perfectly ordered, evenly spaced arrangement of rows and columns, and it makes a wonderful diffraction grating. One that's unbelievably smaller than what we did back on the optics there.
Because it's, on the...
Okay, so our diffraction grating is now going to be a thin piece of some crystal that we borrowed from Mr. Ramsey. Okay, so now these openings are really, really small. They're like they're measured in angstroms, which is a unit that we're going to start using here. Anybody from chemistry remember what an angstrom is?
To the -8?
No.
Not
Okay,
remember.
that's 10 to the -10 meters. Okay. All right, so we go shooting these electrons through the crystal, and surprise, surprise, all of a sudden we get a diffraction pattern. Okay? So,
Are you serious?
yeah, serious, we get a diffraction pattern.
Wait.
Would I lie to you?
Yes.
Yes.
Yeah.
Yes, I would.
Yeah.
But I'm not lying this time. Okay? So what happens is we get a diffraction pattern.
Oh, no.
We get that thing right there, and then it's dark here, and then it's bright up here, and then another one up here. So if that was the way that we proved the light was a wave, what does this mean about matter?
It means that that's a wave.
It means that matter is a wave too.
What? Wait, no. Yeah.
I'll be made of waves.
I warned you that there was going to be pieces of brains lying on the floor here.
Wait.
We're made of waves.
We have not learned.
Hey.
And we're just getting started.
Oh.
Okay.
Why would we have never learned this before? I've never.
Well, I mean, people allude to it that are like, yeah, it's kind of like that, and you're like, wait.
Well, you took chemistry.
Yeah.
You should have talked about this in your chemistry class.
We didn't talk about that it's a wave.
Okay. Well,
No.
okay. Well, that's the reason you come to school is to learn new stuff. Okay. So electrons are actually waves. They are not particles like your junior high school teacher told you. And when they repeated this experiment with protons and other massive particles besides just electrons, they found out that protons and other things are also waves too. So your body is actually made up of a whole bunch of little waves. All of the universe is waves. That's why I warned you back a couple months ago when we first started into waves. I told you that you've got to understand waves because everything in the universe is actually a wave, even your body.
That's crazy.
All right, so now,
I don't feel like a wave.
Yeah, me either, but we are. Okay, so guys. All right, so scientists did a bunch of experiments because they wanted to understand about the waves. Right? So now with electrons, we can shoot electrons at different speeds. If we change the voltage here, that's going to change the speed that the electron is coming out. And you guys have already done some homework problems so that hopefully you understand that. I'll give you, in just a few minutes, I'll give you a problem just to review to make sure you do. But you understand that we can definitely shoot electrons at different speeds, right?
Yes.
Okay, so scientists did a bunch of experiments, and they shot these electrons through the diffraction grating, and they measured these same things that you guys measured when we did the lab ourselves. So this here was L, and this was X, and this was H. Then you can measure what theta was, and you guys remember how it worked.
Yes.
Okay. So they were able to measure the wavelength, and what they found was that the wavelength depended on the velocity of the electron. So the wavelength was proportional to 1 over the velocity. Okay? Yeah, we don't like proportions. But before we take that step, okay, they also played around with different masses. Because in addition to shooting electrons, it's also possible to shoot protons and other things that you guys know in the hadron colliders and the linear particle accelerators. You can shoot more than just electrons. So they shot objects of different mass, and they found out that the wavelength was proportional to 1 over the mass, just like it was 1 over the velocity. Okay?
But then
So-
the velocity and the mass be proportional to each other.
Well, they both come into the equation.
That's
Okay, so the wavelength then they found is proportional to 1 over mv. Okay? All right, so now, Amy, go ahead and say what you just said a few seconds ago. We don't like proportions, we like
so
equal signs. So we have to add a constant into there. And how do we determine the value of the constant? Experiments. All right, so I am going to give you the data from an experiment that was done, and you are going to calculate what the value of that constant is. So,
this is so weird.
let's say that we use a 9-volt battery. We're shooting electrons, so you know the mass of an electron, you know the charge of an electron. So you should be able to calculate what the velocity of that electron is. Okay? And you know the mass of the electron. So if I tell you what the wavelength was, you should be able to then calculate what the proportionality constant is. All right, so if we're using a 9-volt battery and we're shooting electrons, then it turns out that the wavelength that they got was 4.09 angstroms, which is times 10 to the negative 10. So 4.09 times 10 to the negative 10 meters, that's what they got for the wavelength. So knowing that for the wavelength, and knowing that it was 9 volts, and knowing that it was electrons we were shooting, I want you guys to calculate K. I'll give you 3 or 4 minutes to do that. You can pause the video. I need a volunteer to come up and do this one for us. Okay, no volunteers. Chloe, how about you? You want to do this
Sure.
one? You realize you're going to be on video. You're okay with that?
Yeah.
Okay.
Yeah.
Wow, that's not cool.
Uh-huh. So lots of people, their heads are popping left and right here. Okay, let's do it over here. Okay, so voltage is the KE over Q. Okay, so what is KE then? Oh, which is 1/2. Oh, now, okay, yeah, okay, good. Yeah, I see what you're doing. Fine.
Is that okay?
Yeah, that's fine.
Okay.
All right? Well, we need to do some algebra here. Let's solve for V.
Oh, okay.
It's a whole lot easier to do the algebra using the letters than the numbers.
I just,
Okay. Now, we could divide by 1/2, but it's easier to just multiply by 2. Yeah, I agree with that. Okay, then cross that out. Okay, and then we divide by m. Okay, good. And then take the square root of it. Okay, good. All right. So, V is 9. Q is 1.602 times 10 to the negative 19. And by the way, let's call this 9.00. What's the mass of an electron?
9.19 times 10 to the negative 31.
Okay, and those are all standard physics units. Okay, good. So did you plug that in your calculator?
No, I didn't.
All right, so Reagan, thanks, you did a good job.
Oh.
Okay, so Reagan, when you plugged that in your calculator, what number did you get?
6.626 times 10 to the negative 34.
There you go. So that's the proportionality constant that the scientists discovered. 6.626 times 10 to the negative 34. That number looks familiar. Where have I seen that number before?
It's the speed of light.
Constants.
Wait, is that K?
What?
Yeah, that's
Yeah, so that's the K value here.
I still think it's plain.
Okay.
Yeah, see.
So this number here turns out to be the number that's so important that we gave it its own special letter. We called it H, and it was 6.626 times 10 to the negative 34. Isn't that an amazing coincidence?
It's
Yes.
not a
Is it?
coincidence.
I don't know if it is a coincidence. If we knew it was a wave already,
Mm-hmm.
I just feel like it would
You
be
don't know if it was a coincidence. What are the
Okay.
chances of it being?
What are the chances of it being coincidence? Now let's take a minute, because I want you guys to really appreciate how amazing this turns out to be. So, where did we get Planck's constant before? What were we experimenting with?
The
Light,
threshold.
right? Yeah, we were talking about light, which is basically energy. And we found from experiment, we found that the
The slope
energy
is equal to.
the energy was proportional to the frequency, and when we did a bunch of experiments, we found out that the proportionality constant was 6.626 times 10 to the negative 34. This was energy that we were dealing with. Now these guys over here, they are not dealing with energy, they're dealing with matter. Matter is a completely, totally separate thing. There's no connection, right? Matter is something that you can pick up and hold it in your hand.
Or is it?
Whereas energy, you can't pick up energy and hold it in your hand. These are totally different things.
What if they're both wood?
And yet, here we are when we're doing experiments with matter, we find that the wavelength is proportional to 1 over mv. And when we do the experiment, we find out that that proportionality constant is that same number that we called h, 6.626 times 10 to the negative 34. What an amazing coincidence.
Oh my.
Now, at this point, you guys should respond by saying coincidence.
I know.
Yes, and I would be inclined to agree with you. In fact, I would be forced to agree with you. There is no way in the world that that can be just a coincidence. Okay? The inescapable conclusion is that there must be some connection between energy and matter that we had not previously suspected. If only we could come up with an equation that would tell us how energy and matter are related. So, let's see, who hasn't been to
Is
the
it
board
E
in a
equals
while?
MC squared?
I don't know. Anybody want to, Miriam, you want to be the one who derives the most famous equation in all of physics?
Equals MC squared.
Okay.
Is that gonna be it?
I
It's
don't
gonna
know.
be it. That makes the most sense.
Yes, this is a derivation that might very well be on the test.
That's equals MC.
So do you want me to get
Wait,
these sides and then make them equal to each
Okay,
other?
hold on a second. Okay, are we ready?
Yes.
Okay, so first, okay, so this could very well be a question on our next test. Wink, wink, nod, nod. Nudge, nudge. This is not in the book. Okay, so let's start with these two equations. So let's start with E equals HF, which is an experimentally determined relationship that applied for energy. And then over here, let's start with the other equation, which is lambda equals h over mv. Okay? And so Marion, you just play around with those equations and see if you can combine them together somehow.
Sure.
So what's she doing here? Okay, looks like she's going to solve both sides for h, or okay, so she solved both sides for h. Now what are you going to do, Marion? Okay, looks like she's going to set those two things equal. Okay. All right, so if this equals h and this also equals h, then that means this must equal that. Very good. Okay. All right, so let's solve for E. Okay. Can we do any simplification here? What's the relationship between lambda and f? Okay.
So lambda is.
Lambda f equals c.
Oh no.
I'm so excited.
Okay, good. Now, the v here, if this matters,
If it's a wave, and so it's gonna be E equals
Oh, no.
MC squared.
what she said.
I like this.
Okay? Okay, so E equals mc squared. That, yes, it was disappointingly simple, right?
Yes.
A little too simple.
Okay. So, pretty much everybody that I've ever met thinks that this E equals mc squared thing was just, you know, a revelation that nobody can figure out how Einstein came up with it. He must have been a super genius. Well, he was a super genius, but he didn't have to be to do this. This was actually one of the easiest derivations we've done all year.
Yeah.
Wow.
All we needed to know was that when scientists did experiments with light, they got this relationship. When they did experiments with energy or with mass, they got this relationship. They noticed that the proportionality constant was the same, and they figured that probably is not just a coincidence. And from that point on, you can hand it over to a high school freshman in first year algebra, and that first year algebra student can take it from there and derive E equals mc squared. Disappointingly simple.
I like
Okay? All right. Okay. So, in many of your homework problems tonight, all you're going to have to know is this equation here, that lambda equals h over mv. This will be the equation that will solve most of your homework problems tonight. It'll give you different masses, different velocities, calculate the wavelength. That'll be simple, that'll be boring. So let's do some more stuff. Let's talk about the implications of matter being a wave and not a particle. It has huge implications. Like, for instance, any of you have a flash memory stick in your pocket? Or maybe you've got, in fact, for sure, you've got flash memory in your camera.
I have one in my
Okay.
backpack.
You have one in your backpack. How does flash memory work? It works because of quantum mechanics. Okay? If electrons were particles instead of waves, your flash memory would not work. So let's talk about that. All right, so we said that an electron is a wave. Okay, now when you hear the word wave, you think of that. That is the classical wave. Okay. Now,
Is it photons too?
yeah, with photons, is a photon a classical wave?
No.
No, a photon is not. A photon is a little
Wave packet.
wave packet. Do not call it a particle, not in this classroom.
Particle.
I realize your books call it particles and other physics teachers are going to call it particles, but in this classroom you're not allowed to call light a particle. Call it a... Somebody's asking for trouble. Okay. So we're going to call it a wave bundle, or we might want to call it a wave packet.
Or wave burp.
A wave burp, I like that. That's great. I like a wave burp. Okay. Or we can call it a photon. Okay, and just understand that that's what a photon is. An electron is the same thing. An electron is not this classical wave. An electron is a localized wave bundle. Okay, so it's going to look something like this. Okay, so this is an electron. Okay. And this is not just a mathematical approximation or mathematical simplification. It literally is a wave. Empty space is not empty. There is a fabric there. And the electron is a disturbance in that fabric. And so are protons and everything else. Okay? But it's a localized thing. Now, the size of that electron varies depending on how fast it's moving. Remember that lambda equals h over mv. So if v is really large, then what happens to lambda?
It's gonna be
It's really small. Okay? So this electron that used to look like that is now going to look like this. Let's see, it's 1, 2, 3, 4. Now I don't know off the top of my head how many waves are in an electron. I know that for photons, the photons that are coming from these lights over your head, the size of the photon is somewhere between 10 and 20 wavelengths. So in order to be completely correct, I should put a couple more squiggles in here. But let's just, for right now, for artistic sake, let's assume that this photon or this electron is 4 bumps here. So if it's moving really fast, it has a shorter wavelength. That means these bumps are going to be closer together. Okay? So the electron is now more localized than it was if it was moving more slowly. So if I were to ask the question, where is the electron? Well, if it's moving slowly, the electron is somewhere in this space here, where if it's moving fast, it's somewhere in this smaller space here. So the question of where is the electron depends on how fast the electron is moving.
So it's like the Heisenberg uncertainty.
That's it exactly, what he said. Say that again, louder.
Heisenberg uncertainty.
So this is the famous Heisenberg uncertainty principle.
Heisenberg.
Okay. Okay, so this guy named Heisenberg, he quickly realized that if electrons are waves, then the question of where is the electron becomes very difficult to answer. And it becomes a function of how fast the electron is moving, and also its mass. It's a function of its momentum. Okay? So basically the way it works is this. If I were to take a probe, and I were to stick a probe into this region where the electron is, okay, there is a certain probability that my probe will detect the electron. Okay? And it becomes a probability game. So if I put it here, there's a relatively high probability that my probe will report that there's an electron. If I put it over here on the edge of the wave, there is a lower probability that the probe is going to report an electron. What if I put it out here? What happens? What are the odds that my probe is going to? Well, is it 0 or does it approach 0?
It approaches 0.
Yeah, I mean, if you look at a graph where it's asymptotic to the axis,
Yeah.
at some point it gets really, really small, but does it ever really get to 0?
No, it's
So the same thing happens with an electron. Okay? That wave goes down and it gets really close to 0, but it never really reaches 0. So here's where things get fun. Let's suppose that I want to take an electron and I want to put it in a box. In fact, when you guys get to college, the particle in a box problem is a classic problem. You will certainly be doing this when you take quantum mechanics. So I've got a box here, and I've got an electron in it. Now, according to classical theory, the electron is a little particle, and he's right there, and he's in the box, and this is a box that he cannot get out of. The walls are impenetrable. That electron is going to stay in that box forever. But now that we know that classical theory is wrong, so now, and by the way, let's call it classical mechanics, okay? Because mechanics is the study of moving things. So classical mechanics says that that particle cannot get out of that box. But we know that classical mechanics now is not correct. We know that now the world really runs on quantum mechanics. And so this particle that we put in the box is, or this electron that we put in a box is not a particle, it's actually a wave. Okay? And so if we put our probe right here, just outside the box, there is a very, very, very small chance that we will detect that electron, but very, very small does not mean zero. So there's a small but non-zero probability of detecting the electron.
That's crazy.
Okay. So, what does that have to do with the flash memory stick in your pocket? Well, that is how flash memory works. The fact that this electron can escape the unescapable box due to this effect right here, this is called quantum tunneling. And quantum tunneling is the thing that makes your flash memory work. So,
I don't get how. Yeah, why how does the
well,
wave get out of the box? 'Cause when it,
Well, it doesn't, it approaches zero, but it doesn't get there.
yeah. Okay, so we got two questions. One is how does flash memory work? But it sounds to me like we need to address this other
Yeah,
question.
that was my question.
So you want to know how does it get out of the box?
No, I get that one.
Okay, but other people don't apparently. Okay, so if this electron has a wave function that extends out asymptotically to zero, but it never actually reaches zero, that means that when I put the probe here, oh, one thing that maybe I should have explained. Okay, so I'm glad you brought this up. This is probably going to take about 5 minutes to explain, but I think it's worth it. It's worth it. Okay. Okay, let's go back to our double slit experiment. So we are shooting electrons through a double slit. In fact, I think I'm going to take 10 minutes to explain this because there aren't enough brains on the floor yet, and I really want to see some more heads explode. So I'm going to explain something.
Wait. I think maybe I know.
What is it?
So molecular, it's like going to the molecular structure, and the electrons can get through it. So it's kind of like tunneling, so they're like little spaces. Is it kind of like that?
But let's go through this because this is even better.
Okay.
Okay. All right. So back in the days when the scientists first started shooting electrons through double slits, or actually through diffraction gratings, and they were seeing the diffraction patterns, some of the scientists said, well, maybe the fact that we're shooting so many electrons through there at one time is causing the electrons to bounce off each other or somehow affect things. And so maybe that's throwing off the results. Let's design an experiment where we only shoot one electron at a time. Okay? So this one electron is being shot at a double slit. And what happens is, on the wall here, we see one electron appear. And that one electron is going to appear in a couple places. There is a high probability that the electron will appear here. Turns out there's like a 0 probability of seeing the electron here. And then then over here where the other bright spot would be, there's a medium probability of seeing it here, and then there's a 0 probability here, and then over here at the next diffracted bright spot, there's there's a smaller but still non-zero.
So that's why it gets like faded out. a little
Yeah,
bit.
exactly. So there's the highest probability here, medium probability here, lower probability here, zero probability in between. But the thing is that the electron, when the electron hits the wall, you only see one electron hit. Okay, so now let's think about it. When this electron is going through the slit, which slit is the electron going through? Well, if it's a particle, it can only go through one. But now we know it's not a particle, it is a wave.
Maybe
Okay.
one of them?
All of them.
So it is in fact not only possible, but it's reality that one electron goes through both slits because it's a wave. Okay? All right, so instead of drawing it as a particle, we have to draw it as a wave, so it goes through both slits.
What?
Oh my god.
Oh.
Okay? So the wave goes through both slits, and it comes out here, and then these two waves, they interfere with each other. Okay? But now here's where it really, really gets weird. Okay? When this wave hits the wall, only one spot on the wall is going to show the effects. Okay? So let's think of it as if it's water. Okay? So if I've got a water wave coming through here, and this is the beach, and I've got people standing on the beach, and we're all talking with, we've all got radios, and we're all talking to each other. Okay? So this wave comes through and it hits the beach. The person who's standing right here, that person is going to say, I just saw a really big wave hit the beach. The person who's standing right here is going to say, I didn't see anything hit the beach. The person who's standing right here is going to say, I saw a medium wave hit the beach. The person here is going to say, I didn't see anything. The person here is going to say, I saw a small wave hit the beach. Right? Does that make sense? Because of the diffraction pattern, that's the way it's going to work. That's not the way it works with electrons. Okay? When we're shooting one electron at a time here, okay, the electron goes through both slits, so it is in fact a wave, but the person here does not say, I saw part of an electron, and the person here say, I saw part of an electron. That's not the way it works. One person and only one person is going to see an electron. Okay?
Why?
And well, because when the wave interacts with the wall, the wave function collapses, and it collapses to a point, and that point is the electron. Okay? So this concept of the wave function collapses, that is a really important thing, and that's where quantum mechanics gets really, really, really weird. So one person and only one person is going to report seeing an electron, and they're going to report seeing an entire electron, not a half of an electron or not a quarter of an electron. They either see the entire electron or they see nothing. And in this case, it becomes a probability game. Okay. If you're shooting one electron through here, you cannot predict with certainty where that electron is going to hit the wall. But you can calculate the probabilities, and those probabilities will turn out, let me just finish. Those probabilities will turn out to be true. So there is a high probability that you will detect the electron in this region. 0 probability here. There's a medium probability of it here, and by the way, same thing on the other side. 0 probability here, and then a lower but non-zero probability here. So it becomes a probability game. And this is something that bothered Einstein a lot. In the early days of quantum mechanics, Einstein hated the idea that you cannot predict with certainty where that electron is going to be. All you can do is the probabilities. You guys may have heard the famous quote that Einstein said. He said, God does not play dice with the universe. Well, later he came to realize that actually she does. Okay? That is in fact the way the universe works. And Einstein finally accepted that, but it took him a while.
This feels like a morally, like, just
deteriorating thing sometimes. It's like when you prove
Okay,
yourself wrong.
So Reagan, you had a question.
So because it's all probability, aren't you gonna get like a lot of different results and like somewhere
Yeah.
it could even look like the central spot isn't the central spot?
Well, okay, the first time you shoot an electron through, he's going to hit the wall maybe here, maybe here, maybe here.
Yes.
The second time, you know, he hit maybe here, maybe here.
Exactly.
And by the way, same on the other side.
And so,
So if you shoot them through here one at a time, but you shoot, you know, several thousand of them,
okay, so.
eventually, after several thousand of them have gone through, if you were to plot how many times they hit the wall in certain locations, you'll come up with a graph that'll look like this.
Yeah, that makes sense, because if the sample size is big enough, they're probably small.
Yeah, but never becomes 100% sure. Either
Yeah.
way, like, no matter how many you have.
that why-
This is weird, because it's like
there's
applied
that
to
small
statistics
possibility you
though.
would not even like hit in that area.
Yeah. But for any one electron, if you were to ask where is that one electron going to hit, you cannot say. All you can do is say, well, there's a probability that it'll hit here and a probability it'll hit there. Okay? And this is all related to the Heisenberg uncertainty principle. So the universe cannot be predicted on the atomic level. What you can do is you can take billions of atoms and use statistics, and you can predict very, very reliably what's going to happen for those billions of atoms. But for one atom by itself, you cannot predict with certainty what's going to happen to it. So God
One
really
atom?
does play dice with the universe. Okay, so now let's get back to the other thing, and so now the other thing will make sense. Let's get back to the particle in a box.
Wait, does that mean there's like this like really small probability that like everything will just like explode or something?
Yes.
Okay.
Okay. Now, what's the probability that every little molecule would explode at the same time? That's so close to zero, you can call it zero. But inside your body, the one little particle of your body is just going to kind of like just disappear and appear somewhere else. Okay. So okay. Hold on a second.
What do you quartz come into the situation like?
That's different. Let's finish this before we get into that. Let's get back to.
We need to finish this and do flash memory, and then we'll get to that. Because I want to know flash memory.
Okay. So the particle in a box situation is the heart of how flash memory works. Okay. So we've got this particle in a box, except it's not a particle anymore. It's actually an electron, which is a wave bundle. Okay. But we're going to call it a particle in a box just because that's what they call it. Okay. So it's actually a wave bundle in a box. Okay. So if we were to plot the okay. So if it's a little bit closer to the left, it's going to look like this. If we're closer to the right, it's going to look like this. Okay. And so we ask, where is the wave? Well, if we kind of take the envelope right there, if we were to stick our probe right here, then when we detect the electron, what's happening is that the wave function is collapsing, and it's collapsing at the point where our probe is. Okay, so it becomes a probability game. If we put the probe right here, there's a high probability that it will tell us that there's an electron. If we put it right here, there's a lower probability. If we put it out here, there is a small but non-zero probability that the probe is going to tell us that there's an electron there. So even though the walls of this box are supposedly impenetrable, quantum mechanics,
I feel like nothing's impenetrable on like a molecular scale.
nothing is impenetrable on a molecular scale. That's the bottom line. So even though this box is one that you think is impenetrable, because of the beauty of quantum mechanics and because of the effect that we call quantum tunneling, that electron actually can escape from the unescapable box. Now the probability of it escaping is extremely low. We're talking like 1 in a billion or something like that, or even lower. But it's not zero. So now, how does that relate to flash memory?
Wait. I have a question.
Uh-huh.
So you said that like the probability for detecting the electron in the middle would be high, but I feel like it'd be low even if it's in the middle. Like, what's the chances of it collapsing on the probe even if it's in the wave bundle?
Well, think of it like a bubble, a soap bubble. If you stick a probe in a soap bubble, it
Then it will
pops,
pop.
right? Yeah.
Okay, but if you stick it to the side, it'll be like less like a
Yeah, that's a good way to think about it.
Okay.
Now, a University of Utah, or a university physics professor would tell you that I'm oversimplifying things, but that's okay.
That's okay, he's a university.
Yeah. I mean, you're high school students.
We gotta figure out our lives too.
Okay. All right. Before I tell you how flash memory works, let's go back and let's review how the old kind of memory works. You know, this is the kind that we talked about the other day. Okay? So we have a slab of silicon.
Okay, yeah, this is
Okay?
how we get the zeros and ones for like computers and stuff.
Yeah, exactly. The zeros and ones. Okay. All right. So we have this slab of silicon. So let's assume this is it. This is a chip made out of silicon. So if I look down from the top, I see this, but we're not looking from the top. We're looking side on. Okay. So this is a cross-section view. Okay. So how did we do it last time? Well, we took some regions in the silicon where we doped in some impurities. Okay, so these are impurities are doped in here and here. And so if the impurities are there, what does that mean? Is it a conductor or an insulator?
Conductor.
Okay, so where the impurities are is a conductor. Where it's pure silicon, what is it?
Insulator.
It's an insulator. Okay, so let me get this, I want to keep my picture clean, so let me get that out of there. Okay, so then what did we put right here?
Glass.
Okay, a very thin layer of an insulator. Okay. And what did we put right here?
Metal.
Metal. Okay.
Well,
Or-
it's not charged yet.
Not yet. And by the way, it doesn't have to be metal. It could be anything that's a conductor. Okay.
Like human skill.
Okay. All right. Okay, like that. Okay.
And then.
All right.
That was terrible start.
Hey, guys. Okay. So this was what we called the transistor.
Yes.
And it was a gate. It's a gate that we can open and close. How do we open it?
By turning the battery on and off.
Okay, so if we put positive charges on the gate here, on the upper part of the gate, then an effect comes in called
Induction.
charging by induction. Okay, so the electrons that were normally down here,
Are gonna be.
they get pulled up here, and so we have excess electrons here. Those excess electrons act like an impurity. And so this region here, the gate region that used to be non-conductive, becomes conductive. So now if we want to send charges through here over to here, we can do that. So we're going to drill a hole right here. We're going to take a layer of metal that we put on top of there. So this is all metal.
Yes.
So we've opened up the gate by putting the charges on here. So now we can let charges flow through here. So now we get a whole bunch of charges on this region here. By the way, what did we call this part?
The
We
capacitor.
call it a capacitor. Okay. So now we've put a whole bunch of charges on the capacitor. How do we close the gate so they can't get out?
We take the positive charge off of the metal.
Okay, so we take the positive charge off the metal. That means these electrons here, what do they do?
They're gonna combine, like, well, not combine, disperse
go
back
back
together.
Yeah, so they go back down here to where they came before. The gate is now closed. These guys cannot get out. Okay, so we now have 1 bit in a memory chip. Okay, so this transistor and capacitor pair together form 1 bit. So this would be either a 0 or a 1, and then our music or our photograph or whatever we're storing is a whole bunch of zeros and ones. So that means we have to have millions or even billions of bits to store just 1 photograph. But that's okay, we can make these small. Okay. But the problem is that this actually takes up more real estate than we would like. I mean, if you want to make your memory chip hold more and more and more and more memory, more and more and more bits, you're going to have to figure out a way to squeeze this down to a smaller thing. Okay, so this is the old style. Okay, and this is called a DRAM. Those of you that are in computers know that's dynamic random access memory, which, by the way, is still used for certain parts of the computer where you want something really fast. DRAM is still used. But if you want to store something for a long time, and you want to make it as dense as you possibly can, this thing takes up too much real estate. So, we're going to look at the new style of memory, and this is called flash memory. So we're going to start with that same silicon chip that we had before. Okay. But we want to somehow do away with this capacitor, because it just takes up too much space. Right? So we want to squeeze in more things. So, let's take this same insulator that we had before. Okay? Let's take this same metal layer that we had before. But now, let's put another insulator on top of the metal. And let's put another slab of metal on top of that. And by the way, it doesn't have to be metal, it can be anything conductive. And actually, in real life, they use polysilicon. Let's not get into that. Wait, let's call it metal. Okay. All right, so now, this piece of metal right here, I need to give it a name to distinguish it from the other one. So I'm going to call this one the floating gate. And this piece of metal up on top, I'm going to call it the control gate. Okay? Now, I'm going to take my wire and I'm going to connect it to the control gate. So I can put charges on the control gate. I can put positive charges on there, I can put negative charges on there, I can do anything I want. Can those charges get through the insulator down into the floating gate?
No.
Well, not according to classical mechanics.
Oh, but they can.
But can they, now that we know about quantum mechanics?
Everything we learned was a lie.
Everything we learned was a lie. But it was a useful lie because it was helpful for understanding things at the time. Okay, now that we know about quantum mechanics, we know that it actually is possible, thanks to the wonders of quantum tunneling. Okay. If I were to put a whole bunch of negative charges on the thing here, okay, so electrons are just negative charges. If I were to load this up with billions and billions of electrons, and if this insulator here is thin enough, quantum mechanics tells us that a few of all those electrons can tunnel through, and so let me make it look like this. Okay, so a few of those electrons can tunnel through the oxide and can get into the floating gate. Quantum mechanics allows this. Classical did not, but quantum mechanics does. Okay. Now, the odds of an electron getting through are really small, so in order to get some through, I'm going to have to put a whole lot of electrons up here, but I can do that. So some of them now get through. Okay. This now becomes my 0 or my 1 in my memory. So if there are electrons down in the floating gate, that would be considered a 1. If there aren't electrons in the floating gate, that would be considered a 0.
And you can just put those next to each other like...
Yeah, and I can put a whole bunch of these. In the same space where I had one bit before, I can fit a whole bunch of bits into that same space
Wait,
now.
what is the silicon?
Ah, okay, so good question. Why are we bothering to do this on top of a silicon chip? Okay, well, okay, so let's figure out, how do we know whether there is charge in the floating gate?
Oh, I get it. So now it's like if the positive charges go up and the negative charges go down on the silicon, then we can tell that if it's charged, because then the electrons get through or not.
What she said. Okay, that's exactly it.
Wait, say that again.
Okay, so let me draw a picture, because a picture is worth 1,000 words.
Yeah, it's
Okay.
dispersed, the positive and negative.
So Reagan is recognizing that once we take off all these charges here, okay, and so here we have our gate up here, and here's our gate down here. We don't have very many electrons there. How do we know that we have electrons there? So Reagan is suggesting But let's go back and let's do the same trick that we had over here. Let's build a transistor. Let's dope some regions on the left side and on the right side. Okay. And let's connect a wire. Let me do this wire in a different color. Let's take a wire and let's solder it onto there, or connect it by some other means. And we connect it over to here. Okay. So, if electricity can flow through the wire, then we know that there must be some charges in the floating gate. How is that? Because if there are charges in the floating gate, what's going to happen in the gate region underneath here?
It's going to charge.
Now in this case, if these guys are negative, then what's going to happen is we're going to have positive charges. Whereas over here I showed it as being negative, but it doesn't matter. A positive charge down there is going to act like an impurity, just like the negative charge did over here. And so if we have electrons in our floating gate, then it attracts positive charges and the electricity can flow through our transistor, and we know that we have charges there. If, on the other hand, we try to flow electricity through here, but the electricity can't flow through there, it's because we don't have charges down here, and that would be because we don't have charges up there. Therefore, using this transistor, so we still have a transistor. We just don't have the capacitor anymore. Okay? So we use the transistor in order to read whether or not we have a 1 or a 0. Okay? So this is how flash memory works, and it's all thanks to the wonders of quantum mechanics, specifically quantum tunneling.
That makes perfect sense.
Yeah, it's easy. If you understand a few basic concepts, all of this magical semiconductor stuff becomes non-magical. It becomes, whoa, that's obvious, that's easy. Why didn't somebody think of that before? So now we need to know that Ben Franklin did in fact get it wrong. So if we put positive charges on here, they are going to behave differently than negative charges would. So now we have to realize that the charge carrier is actually the electron, which is actually the negative one. So if we want those electrons to tunnel, we want to put negative charges there.
Okay.
How fast would they have to be traveling?
Well, it's not so much how fast they're traveling.
It's just probability.
It's just how many of them do you have there. Let's assume that 1 electron out of 1 billion is going to quantum tunnel. Okay, so if we have 1 billion electrons up here, 1 of them is going to quantum tunnel down there. Now you might say, once we take these charges off, what prevents the electron from quantum tunneling its way out? Well, we don't have billions of them down here. We only have a few electrons down there. And since the probability of them tunneling out is like 1 in a billion, which is, by the way, a number I'm just making up, okay? But if it's really, really small and we don't have very many electrons, they're not going to tunnel out. But now this is an important thing. Given enough time, they will tunnel out. Okay, so let me just finish one thing, then I'll take your comments. So this flash memory that I have in my pocket here will not last forever. Given enough time, these electrons will in fact tunnel their way out. So a flash memory stick, if you want to keep something for 100 years, don't put them on flash memory. If you want to keep it for 1 year, oh yeah, fine. And in fact, the flash memory that is being sold these days, you can keep stuff on there for like 10 or 15, maybe even 20 years. But don't try to keep it any longer than that, because they will in fact tunnel their way out. So now, hold on. So we had some questions there. So, okay, let's start.
Okay,
here.
so why is it that when you don't eject a flash drive properly, that it sometimes gets really messed up?
Oh, that has to do with computers. That has nothing to do with physics. That's just the way computers work.
Okay.
So wait, it will get out eventually. Is that because even if there's a small amount, it keeps moving. It keeps
Right.
moving, and so then it's 3, but then 3 keep moving, so then it keeps adding. So it's
Right.
practically there's a large
Yeah.
amount that it is.
So think of it as the particle in the box here. The particle in the box, which is really a wave in a box, when it comes over and hits the wall, the probability of it tunneling through the wall
Yeah,
is
but
like
then-
1 in a billion, so it
But
doesn't
then
happen.
it doesn't hit the wall, so then it reflects, so then it hits
Yeah.
that, and
So after it has hit the wall 1 billion times, there's a good chance that on one of those billion tries, it will in fact tunnel through the wall.
So where would you want to store your memory if you wanted to keep it longer than
Well, yeah, if you want to archive memory forever, probably a CD or a DVD would be the way to do it. Then you burn a little hole in the CD, or not a hole, but just burn a little spot in the CD. And then that burn spot will stay there for a long, 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 long time.
Wow.
All right?
Everything is temporary.
What is called?
All we are is dust in the wind, yeah. Okay. All right? Okay, so that is a quick,
That was great.
quick introduction to quantum mechanics and the uncertainty principle and quantum tunneling. And by the way, none of this stuff is discussed in your book. Shame on them.
Does that mean our physics homework won't be on it?
Well, there won't be, tonight's homework will not cover any of this, but I guarantee you, there will be a question on the test this related to this.
I liked it.
So I hope you've got it in your notes
You're
somewhere.
like gonna like just walk out and be like, everything is temporary.
Yeah. So, actually, your brains are surprisingly intact. The 8A class, boy, their heads just exploded. But your guys, for the most part, your heads are intact. That's pretty good to see.
Like, you trained us to like not trust me in general, so it's like, oh, mind blow, I guess.
So, with the whole idea of what would happen, if an unstoppable force met an immovable object, does that mean the unstoppable force would win?
There is no such thing as an immovable object, or in this case, an unescapable box. There is no such thing as an unescapable box.
Which makes sense if you think about it.
Yeah.
See, that's
Okay, so your homework for tonight is on the board,
But the bullet would just
19 through 25. You can stop the video, thank you.